So in this video, I want to explain the EPR paradox, which is a paradox proposed by Einstein, Podolsky, and Rosen back in 1935 to prove their realist position on quantum mechanics. So back in the days, there were three major positions people had, or physicists had, on quantum mechanics. So one's realist, the other one's orthodox, and the other one is agnostic. So for orthodox viewers, so physicists who believe in orthodox view, what happened is that the particles is in a superposition of both position 1 and position 2, and only after the measurement is made or the collapse of the wave function that the actual position of the particle is determined. So that's what they believe. So they believe that fundamentally the world is probabilistic, and that the result is only there after you observe or so-called collapses the wave functions. That's what they believe in. So people like Einstein disapprove that. They don't believe that. So they have this position called the realist position, where they believe that the position of the particles has always been determined, and there is this hidden variable, which is the famous hidden variable theory. So there's this hidden variable that already determined the position of the particle. So realist position would be believing that at the fundamental level, the world is not probabilistic. So these are two opposite views of how people wanted to explain the quantum mechanics or the particles' behavior they were observing in their experiments. So EPR paradox is this paradox by Einstein, Podolsky, and Rosen, all realists, to argue against the orthodox view. So we can first consider the decay of a neutral pi meson into an electron and a positron. So you don't really need to understand what a pi meson means, but what we need to understand is that we have a particle called pi meson, and pi meson decay into a electron and a positron. A positron is basically an electron, but with positive charge. So it has the same mass, same spin. I don't think it's the same magnetic moment, but you can just imagine it to be an electron, but with positive charge instead of negative charge. So this one's the electron, this one's the positron. So we assume that this pion that we have here is at rest, and that the electrons and positron flies off in opposite direction. So that's going to look something like, here in the middle is the pion. So one goes this way, the other one, they go opposite direction. So let's say this one is the electron, this one is the positron. They fly towards opposite direction. Now since a pion has a spin of 0, so the conservation of angular momentum requires that the electron and positron occupy the singlet spin configuration, which is the following. I'm just going to explain this in a moment. So this is the singlet configuration. If you have listened to my previous video, you will instantly identify that this is I talked about this in one of my previous video on identical particles. And since both electron and positron are fermions, when you have identical fermions, it's anti-symmetrical, and their configuration looks like this. So for those that does not understand what I have just said, what this means is that there's two possibilities, which is that our electron is in spin up, our positron is in spin down, or our electron is in spin down, our positron is in spin up. So the total angular momentum requires that the spin to be conserved. So the first one describes one state where, let's say, the first particle is spin up, the second particle is spin down. This states right here says a state where the first particle is spin down, the second one spin up. That's the only two possibility that's going on here, right? So back to the paradox. So if the electron is found to have spin up, the positron must spin down, and vice versa. And quantum mechanics doesn't tell you which combination you get. So in any decay situation, it does says that the measurements will be so-called correlated. So you get a combination half of the time. So quantum mechanics doesn't really tell you, okay, each time, quantum mechanics doesn't really tell you a definite answer to whether electron or positron is going to be the spin up or the spin down. That result is only obtained after you make the measurement. So we can continue with our paradox. So now suppose we let electron and positron fly off in opposite direction. Let's say in principle 10 light years away. Then if you measure the spin of one of them, let's say you measure the spin of the electron here, say you get spin up, immediately you know that somebody 20 light years away will get spin down right here if they measure, if that person examines the positron. And that has a very profound implication, because to the realists, there's nothing surprising about this, right? Because the realists believe that there is a hidden variable that already determined the spin up or the spin down of the electron and the positron. It's just that our human doesn't know about it, right? So the realists are not surprised at the result because the electron really had spin up and the positron really had spin down from the moment they were created. It's just that our quantum mechanics theory doesn't know about it. But this is very problematic for orthodox view, because the orthodox view holds that neither particle had either spin up or spin down until the after measurement event intervened, right? That's what I talk about the orthodox view, is that they believe that we only know the definite result after we make the act of measurement. So this is very problematic for the orthodox view, because your measurement of the electron collapses the wave function and instantaneously produces the spin of the positron 20 light years away, right? So the problem with that is that you have a pion and they decay. So you have an electron and a positron, and their angular momentum has to be conserved. So therefore, one's always going to be spin up, the other one's always going to be spin down. So the orthodox believe that we don't know if they're going to, let's say in this case, the electron's going to be spin up or spin down before we make the act of measurement, and the probability is 50-50. So if you have them fly out like light years away, and you measure the electron, so let's say you measure the electron in this case, you measure it to be spin up, then if somebody else at that moment examines the positron at this end, they're going to find it to be spin down. So somehow that is called a spooky action at a distance, because somehow the particles themselves sort of knew what the other particles did, in that sense that they can be either spin up or spin down. Like they can somehow correlate over such a large distance. We're talking about 20 light years away, and this result is instantaneous. What that means is that what Einstein is trying to argue here is that this sort of instantaneous action between the electron and the positron defies the locality. So what the locality is, what the principle of locality means is that no influence can propagate faster than the speed of light. So that is the problem for the orthodox view, right? Because the orthodox believe that, okay, the electron and the positron are both in a 50-50 spin up, spin down situation, and we only know the result after you measure one of them. And some of the particles, even if they're so far apart, even if you have one particle at one end of the universe, the other one at the other end of the universe, if they're correlated and they did fly that much distance, if you measure one of them, the other one at the other end of the universe over such a large distance would instantly know which one the other one has been measured to be. And that is what Einstein called the spooky action at a distance, because that sort of knowing is instantaneous. So that's his argument against the orthodox view, because he believed, everybody knows that nothing can propagate faster than the speed of light, and in this case it clearly does if the orthodox view were to be right. So however, you could argue that you might be tempted to propose that the collapse of the wave function is not instantaneous but travels at the finite velocity. So is that possible in this case? No, it's not possible, because if you measure the electron, let's say to be spin up, right? And if that reaction is finite velocity, let's say I travel at the speed of light, what's going to happen is that the positron, if we measure the positron before the news of the collapse of the electron had reached it, there will be a 50-50 probability of finding both particles will spin up, right? Because, so let's say, okay, you observe this is spin up, and this, and then this sort of information propagate at a constant speed. Let's say before it even, so it has to go this direction, but before it reaches our positron over here, if you made a measurement, there's still a 50-50% chance, right? So if the reaction or the act of measurement were to be a finite, then it will mean that 50-50 before this news of collapse on the electron reaches the positron, there's a chance that you may also measure spin up on this, and that will violate the angular momentum, because we require one to always be spin up, the other one always to be spin down. So evidently, the collapse of the wave function is indeed instantaneously, that we have measured in numerous experiments up to this point. So at the end of the day, Einstein was indeed wrong on this. And in my next video, I'm going to explain the Bell inequality, which disprove the realist position. And in this video, I didn't really talk about a lot of math, but rather word heavy. But in my next video, I would be talking about a lot of math. So you better be prepared for it. And if you guys have any question about the EPR paradox, feel free to comment down, or I'll see you guys in the next video.